Hello everyone, I am Honar Gupta, currently a PhD student at IIT Kanpur. Today we will discuss about the week 9th of the fundamentals of supersonic and hypersonic flow. In the week 9, mainly the decapitulation of the vibrational and chemical non-equilibrium was done, and the implicit hypersonic non-equilibrium flow was discussed. We will start with some problems. Choose the correct option or options regarding non-equilibrium flow across a normal shock. Statement 1. Flow ahead of shock front is in non-equilibrium. Statement 2. Flow behind the shock front is frozen. Statement 3. For some distance behind the shock front, the flow is in equilibrium, and at the still larger distances, it attains equilibrium. There are 4 options. Option A. Statement 1 true. Statement 2 false. Statement 3 true. Option B. Statement 1 false. Statement 2 true. Statement 3 true. Option C. Statement 1 true. Statement 2 true. Statement 3 true. Option D. Statement 1 false. Statement 2 false. Statement 3 false. So in this problem, there are 3 statements are given, and we have to tell which one is true and which one is false. And it is regarding non-equilibrium flow across a normal shock. So first we should know what is the non-equilibrium flow across the normal shock. The definition of frozen flow, non-equilibrium flow and equilibrium flow I will tell later, but first we will see what happened. You might have studied in the this week's lecture also. So I will directly go to the solution of this problem, and first we have to see what happens across a shock. So this is the shock, normal shock, and if some flow is passing through it with u1 velocity, then what will happen that just after the shock, for a very small length, it will remain in the frozen condition. Frozen means there is no chemical or vibrational, there is not enough time for chemical non-equilibrium. There is no chemical reaction are happening. So due to this frozen flow, it will react like calorically perfect gas. After that, due to this high temperature, the chemical non-equilibrium will start, and a chemical and vibrational non-equilibrium will start, and this flow will be in the non-equilibrium, and it will take some time for this flow to attain equilibrium. So for some distance, let's say x1 to x2, this flow will remain non-equilibrium. This is for non-equilibrium, and after it the flow will attain equilibrium, and it will remain in equilibrium till infinity. So we can see that just after the shock, flow is frozen for very short length, then flow is in non-equilibrium for moderate length. After that, till infinity, this flow will remain in equilibrium. So in the previous problem, if we see, flow ahead of shock front is in non-equilibrium. The flow ahead of shock front means this flow is in non-equilibrium. This is incorrect because this flow is already in equilibrium. The equilibrium flow was coming, and after it what happens is that it's discussed here. So statement 1 is nothing but false. Statement 2. The flow behind the soft front is frozen. If you see here, the flow behind the soft front is frozen, but only for short distance. After that, there is also non-equilibrium and equilibrium also. So this is also false. Statement 3. For some distance behind the soft front, the flow is in non-equilibrium, and at still larger distances, it attains equilibrium. For some distance behind the soft, the flow is in non-equilibrium. After that, it attains equilibrium. So you can see here, this is the correct sentence. So this statement 3 is true. So if we check the option, which one is the correct option? Option D, in which statement 1 and 2 are false and statement 3 is true. Now we will see the next problem. A strong normal soft forms in a stream of molecular nitrogen inducing chemical reactions. Choose the correct option or options concerning this flow problem. Statement 1. The temperature decreases below the frozen temperature value downstream of the soak due to the dissociation of N2 into N. Statement 2. Dissociation is an exothermic reaction. Statement 3. Density increases above frozen density value downstream of the soak. Option A. Statement 1 true, statement 2 true, statement 3 false. Option B. Statement 1 true, statement 2 false, statement 3 true. Option C. Statement 1 false, statement 2 false, statement 3 true. Option D. Statement 1 true, statement 2 false, and statement 3 false. So this problem is also related to true and false of the statement, and it is also related to the normal soak. Only thing is that in this one it is asked what happens to molecular nitrogen when it passes through the soak. So this is normal soak, this is upstream flow, and this is the N2. So what happens to the flow when N2 passes through N? And it is also mentioned that it is inducing chemical reaction. So what will the answer for this problem? Okay, we'll see. So before also we have seen that what happens when a flow passes through a shock wave. First, initially it will remain frozen for very short distance, then non-equilibrium, then equilibrium. Here also, let's say this is the shock front. So one flow is passing through a shock front. So what happens there? We'll see first its temperature. Due to shock wave, its temperature will increase to the for initial distance for this time it will then increase till the frozen temperature for very small distance. After that, you see here, for very far distance it will remain frozen, then it will go in non-equilibrium. So what will happen in non-equilibrium? This N2, it will dissociate into N2, and by the collision of some species M, it will dissociate into N, molecular or atomic nitrogen. So this reaction is endothermic reaction. It means it needs energy for the dissociation. So some of the energy, translation energy, will go to into the dissociation of this N2 molecule. So as translation energy is decreasing, its temperature will start decreasing, and this temperature will start decreasing, and it will keep decreasing till it attains the equilibrium flow. So whenever there is equilibrium, this chemical equilibrium, means there is no more dissociation of nitrogen, and there is vibrational equilibrium also. It will attain the equilibrium, and at that equilibrium temperature will be constant. And if you see that this temperature will be lower than this frozen temperature. Why? Because some of the energy is gone to dissociation. Now if you see the density across a normal source increases, but initially it will be same as the frozen density. Now if we know that P equal to rho RT, or from this you can see density is inversely proportional to temperature. So as the temperature is decreasing in the non-equilibrium region, you can say that this is the non-equilibrium region, this side. In the non-equilibrium region, as temperature is decreasing, the density will increase, and it will be till it attains the equilibrium. At equilibrium, density will become constant. Now we will see what happens to the concentration of nitrogen, atomic nitrogen. Now one thing to note, that is that here in the upstream there is no atomic nitrogen. So in the start, as there is no, initially there is frozen flow just after the shock, so there will be no atomic nitrogen also in the frozen condition. So there will be no change. Generally in the frozen condition there is no change in the concentration of a species. So because there is no chemical reaction happening, so whatever was concentration of nitrogen before the shock, it will remain the same after the shock. So frozen condition will be same as before condition, upstream condition. Now due to the chemical reaction, the nitrogen concentration is increasing. Due to dissociation, nitrogen concentration is increasing, and it will increase till it attains the equilibrium. And equilibrium, this concentration will become constant. This I mentioned it for nitrogen only. If we check for molecular nitrogen, then we will see, so this is the CN2 frozen, then you will see that its concentration will decrease. Till it attains the equilibrium. Now we will see what were the statements. Which one is true and which one is false. Statement 1 was temperature decrease below the frozen temperature value downstream of the swap due to dissociation of N2 into N. First thing is that we have seen that temperature is decreasing below the frozen value. Now, is it due to dissociation? Yes, it is due to dissociation because N2 is dissociation into N. So, as it is endothermic reaction, it will take some of the translation, some of the energy from the flow, maybe due to translational energy from the flow, and which will be used for dissociation. So, as translational energy is decreasing, the temperature will decrease. So, dissociation is the reason for this decreasement in the temperature below the frozen temperature. So, this statement is true. Statement 2. Dissociation is an exothermic reaction. This is wrong because dissociation is an endothermic reaction. Energy is needed for this reaction. It does not give any energy. So this statement is false. Statement 3. Density increases above frozen density value downstream of the shock. This also we have seen temperature was decreasing and the density was increasing in the non-equilibrium region. So the equilibrium density was greater than frozen density. Not only this, downstream of the shock, this density is also greater than frozen density. So this statement is also true. So which option will be correct? Option B, because statement 1 is true, statement 2 is false, and statement 3 is true. Now we will see next problem. Before, two problems were related to inviscid hypersonic non-equilibrium flow, but I will also tell some problem related to non-equilibrium, vibrational non-equilibrium, and chemical non-equilibrium. So this problem is related to that only. If the number of collisions that an O2 molecule must experience to become first vibrationally excited is ZB and second to dissociate into O atom is ZD, then the following is true. For O2, this ZB is always less than ZB. So more collisions are required for the chemical reaction than for vibration excitation, because for the dissociation a minimum amount of energy is also required, and if the molecule is already vibration excited, then for them it is easier to dissociate also, or from happening of some chemical reaction. So the number of collisions required for the chemical dissociation is greater than the number of collisions required for vibration excitation. So option B is correct here. Now we will see the next problem. This is also directly, you can say, if you know the answer, you can directly choose the option in this problem. The vibrational rate equation is given by option A, d E vibration upon dt equal to tau E vibration equilibrium minus E vibration. Option B, d E vibration upon dt equal to 1 upon tau E vibration equilibrium minus E vibration. Option C, d E vibration upon dt equal to tau E vibrational minus E vibrational equilibrium. And option D, d E vibration upon dt equal to 1 upon tau E vibrational minus E vibrational equilibrium. So in this equation, this tau is vibrational relaxation time, and E vibrational equilibrium is nothing but vibrational energy at equilibrium. And E vibration is vibrational energy. So what will be the answer for this problem? So what is the vibrational rate equation? It is d E vibrational upon dt equal to 1 bar tau E vibrational equilibrium minus E vibration. This is the vibrational rate equation. So which option is correct? Option B is the correct. Now we'll see the next problem. The Landau-Taylor rate model expresses the relaxation time as a function of A, temperature and volume, B, volume and pressure, C, temperature and pressure, D, pressure and entropy. So what is this Landau-Taylor rate model, and which relaxation time it expresses? So we have seen the relaxation time, tau, vibrational relaxation time. So this Landau Toller rate model expresses this tau in terms of some of these parameters. So what will be the answer for this problem? So the Landau Toller rate model is given by tau p equal to c1 e to the power c2 on t to the power 1 by 3. Here c1 and c2 are two constants which can be found from the experiments. And it is very difficult to find the C1 and C2, and there might be some uncertainty which exists in this value because these values are found for the high temperature gases, and the facility like soft tube and expansion tube which has very low test time. So there is some large scatter which is invariably available in the values of C1 and C2, which you can see from the various literature also. And if you see the formula for tau also, tau was nothing but 1 by k10 1 minus e to the power minus h mu upon kt. And you can see that this term is directly related to the temperature, and this k10 depends on what? K10 depends on transition probability P and Z, collision frequency. And it is also seen this transition probability and collision frequency, and we have seen before this collision frequency is nothing but depends on reference temperature. So from this also you can see that this relaxation time is function of reference temperature only, or from the equation also you can see that this relaxation time is function of reference temperature. So option C will be the correct option. Now we'll see the next problem. 3 chemical reactions involving non-medium high temperature air are stated below. Reaction 1, N2 plus O2 will give 2n plus O2. Option B, reaction 2, O2 plus N will give N2 plus O. Reaction 3, N plus O will give NO plus E minus. Reaction 1, 2 and 3 respectively belong to the following category. Option A, recombination, dissociation and bimolecular exchange. Option B, dissociation, bimolecular exchange and dissociative recombination. Option C, dissociation, dissociative recombination, displacement. Option D, dissociative recombination, displacement, dissociation. So let's check reaction by reaction. First reaction is N2 plus O2 will give 2N plus O2. If you see this reaction, main change is happening in N2. N2 is changing to 2N. Molecular nitrogen is changing to atomic nitrogen, and O2 is same. So O2 is acting as nothing but collision partner, and this N2 is the dissociation of N2 is happening from N2 to 2N. For this reaction is nothing but dissociation reaction. Second reaction is O2 plus N gives NO plus O. O2 plus N will give NO plus O. You can see here this N2, this O2 and N both are reacting, and one atom of O is combining with N and it is becoming NO. So what is happening here? Bimolecular exchange. Molecular are exchanged between two molecules. And this is what? Bimolecular exchange. Next reaction is N plus O will give NO plus E. One thing you can see, N or O both are combined, so this is nothing but recombination. But this is not N, this is NO plus, and there is one electron also. So NO, the dissociation of NO is happening. So what is this? It is happening, both dissociation and recombination is happening. So this is dissociative recombination. So first reaction is dissociation. Second reaction is bimolecular exchange, and third reaction is dissociative recombination. So which option is correct? Option B is correct. So next problem. When we follow a fluid element crossing a strong normal shock wave, the following statement is or are true. In a small region ahead as well as behind the fog, non-equilibrium conditions prevail. Option B. In a small region behind the fog, non-equilibrium conditions prevail. Option C. The fluid element is at equilibrium condition when it crosses the fog. Option D. Behind the fog, the fluid element will perpetually remain in the state of non-equilibrium. So this is related to normal shock wave. So we have already seen if one flow is passing through the normal shock, first for a small distance it will remain frozen. Then for a moderate length it will be in non-equilibrium. Then it will attain the equilibrium. Why it happens? Because this change in from due to the fog, there is abrupt change in property. So initially the flow will not take much time for the chemical waves. So initially it will remain in the frozen flow. But after that, due to the high temperature, the collision will happen and some of the energy will go to vibrational mode of the molecule. So due to the vibrational mode of the molecule, its vibration energy will increase, and due to the collision, chemical reaction will also happen. So it will have non-equilibrium for some distance, and after that, when it attains the equilibrium once again, it means that vibration and chemical equilibriums are attained, it will remain in equilibrium. So now if you see the options, option in a small region IA as well as behind the fog, non-equilibrium conditions prevail. This is false because there is no non-equilibrium ahead of fog. We have the flow is in 0. So option A is wrong. Option B, in a small region behind the fog, non-equilibrium conditions prevail. You can see that for a small region behind the fog, the non-equilibrium conditions prevail. So you can see that before the non-equilibrium region. So this statement is true. Option C, fluid element is at equilibrium condition when it crosses the fog. This is false. We have already seen first it will remain frozen, then non-equilibrium, then it will attain the equilibrium. Option D, behind the fog, fluid element will perpetually remain in the state of non-equilibrium. This is also false because after some distance it will attain the equilibrium. So the correct option is option B. In a small region behind the fog, non-equilibrium conditions prevail. Now we will see the next problem. This is a very basic question. Vibrational excitation can occur for option A N, atomic nitrogen, option B N2, molecular nitrogen, option C atomic oxygen, option D atomic oxygen, molecular oxygen. So what will the answer for this? Answer for this is option B and option D, because both are molecules. We've already seen that for atoms there will be translational energy and electronic, and only for molecules there will be translational, rotational, vibrational and electronic mode of energy. So vibrational energy excitation can only occur for molecules. So in these options, what are the molecules? N2 and O2. So only for this molecule vibrational excitation will occur. We will see the next problem. Following is the correct form of the relation between reciprocal vibrational rate constants. A k I minus 1 comma I equal to k I minus 1 e to the power minus h upon kt. Option B, k I minus 1 equal to k I minus 1 comma I e to the power minus h upon kt. Option C, k I minus 1 comma I k I minus 1 e to the power h upon kt. Option D, k I minus 1 comma I equal to k I minus 1 e to the power minus 2 h upon kt. Here k I minus 1 comma I is what? This is nothing but vibrational rate constant. Vibrational rate constant for transition from I minus 1 level to ith level. Similarly, k I minus 1 is what? Vibrational rate constant for transition from ith level to I minus 1 level. So what will the answer for this problem? So we will write this relation. If you remember the relation, it is very straightforward. So let's say there are two levels, I minus 1 and I, by different energy level. So the particle is going from ith level to I minus 1 level, and from I minus level to I it is coming. So the number of particles which go from ith level to I minus level and the number of particles which goes from ith to a minus level, and number of particles which goes from I minus level to I. Both should be equal in equilibrium flow. So what will happen? First, we will see what is the rate of change of particle in ith level. We don't need to write this. So what are the number of particles which are going from ith level to I minus level? It will be ki I minus 1 into n. Number of particles dropping from ith level to I minus 1 level per second. And k I minus 1 to I into n I minus 1 is what? Number of particles going from I minus 1th level to ith level per second. So in equilibrium, what will happen? Both will be equal. So k I minus 1 comma I and I minus 1 equal to, for equilibrium I will start k I comma I minus 1 and I start. Now from Boltzmann equation, sorry, from Boltzmann statistics, we got that the Ni star, what is the Ni star? From Boltzmann distribution, Ni star will be equal to n gi into the minus epsilon I upon Qt upon Q. So what will be Ni star on Ni minus 1 star? e to the power minus epsilon I upon kT upon e to the power minus epsilon I minus 1 on kT. Degeneracy will be the same for both levels, and we know that epsilon I equal to h nu I h nu. And epsilon I minus 1 equal to I minus 1 h nu. It will be to the power minus epsilon I minus epsilon I minus 1 upon kT. So both their difference will be epsilon I minus epsilon I minus 1 will be equal to h nu. So ni star upon ni minus 1 star equal to e to the power minus h nu upon kT. If you see this equation, let's say equation 1. So equation 1 can be written as ki minus 1 comma I equal to ki comma I minus 1 ni star upon ni minus 1 star. If we substitute this value, then we get ki minus 1 e to the power minus h nu upon kT. So in the option, if you see, it is famous option here. Ki minus 1 comma I equal to ki minus 1 e to the power minus h nu upon kT. Now there is one more thing, which is what now we'll discuss in theory. So one of the topic is coupling between vibrational non-equilibrium and chemical non-equilibrium. So what will happen generally if both vibrational non-excitation, or you can say vibrational non-equilibrium, chemical non-equilibrium, both are present in the gas, then there will be coupling between chemical reaction rate and vibrational reaction rate. So the value of this vibrational relaxation rate will affect the chemical relaxation rate and vice versa. So if molecule which are highly excited vibrationally dissociated by collisions. So if they are already vibrationally excited, they require very less energy to dissociate during the collision. So the chemical reaction rate for dissociation are going to be faster if gas is already in the vibrationally excited state. And the dissociation more readily occurs in the highly higher if particles are present in the higher level of vibrational levels. So if the particles or molecules on the higher vibration levels are gone for the chemical reactions, then that population will decrease. Due to that, vibration reaction rate will also be affected. So if there is there is a strong coupling between vibrational non-equilibrium and chemical non-equilibrium. So for this coupling is very complex. So to use this coupling, Park has given two temperature model. So in two temperature model, one temperature is T translational temperature, and that is vibrational temperature. And the instantaneous vibrational temperature is given by using the vibrational energy, and we know that vibration energy is given by h nu upon q t, where we will use the vibrational temperature upon e to the power h nu upon q t vibrational minus 1 into r t vibration. So using this instantaneous vibration energy, we can find the instantaneous vibrational temperature. So the higher this vibrational temperature, the more will be the particle which will be in the higher vibrational energy level, and it will be more easier for them to dissociate. So to account for this effect in the chemical reaction, chemical rating constant, Park has given one mean temperature which is defined with the geometric mean of translational and vibrational temperature. So T equal to under root T vibration into T. So when in equilibrium, T vibrational will be equal to T, which means TA will also be equal to T. So if there is equilibrium, then T vibrational and TA will be the same. And in non-equilibrium only, this TA will be different from the T. So if TA is greater than T, or T vibration is greater than T, then the chemical reaction will be the faster. And if T vibrational is less than T, or TA is less than T, then chemical reaction rate will be slower. Even if this vibration effect non-equilibrium is already present, but this is about the chemical non-equilibrium. So if the vibrational temperature is less than translational temperature, then chemical reaction will be slow. Chemical reaction rate will be slow. So this is the two temperature model, the part which is used for the coupling between vibrational non-equilibrium and chemical non-equilibrium. Now we will see what is the frozen non-equilibrium and equilibrium flow. This we have studied many times also, and in many lectures also. So first we will see what is the frozen flow. So in frozen flow, the chemical reaction rate are 0 and vibration relaxation time is infinite. So it means to say that there is no chemical reaction are happening and there is no vibrational excitation. For the frozen flow. And equilibrium flow, in equilibrium flow, chemical reaction rate are infinite and vibrational relaxation time is 0. So in equilibrium flow, the if flow is happening, then it will instantaneously adjust to the equilibrium flow if any changes were happening to it. Let's say if there is some chemical reaction also, then it will attain instantaneously equilibrium. Let's say there is flow is happening. So in each point of the flow, it has different referent temperature, and due to which chemical reaction is happening, but at the next point of the flow, it will attain equilibrium automatically, not attaining instantaneously. So it does not take time for the chemical reaction and vibrational excitation to occur. But we already know that it is not possible that there is no that flow is completely frozen, like there is no chemical reaction or no vibrational excitation occur, or the flow is equilibrium, like there is no time for taken for the chemical reaction or vibrational excitation. So flow, our real flow is always the equilibrium flow. Sorry, non-equilibrium flow. So in non-equilibrium flow, suppose chemical reaction and vibrational excitation is happening. But For our convenience, we define the equilibrium and frozen flow using the characteristics time. Let's say tau f is the characteristic time of flow, which is known by L upon V infinity. L is the characteristic length and V infinity is the resting velocity. And tau c equal to is characteristic time of chemical reaction or vibrational energy to reach equilibrium. So if tau f is very greater than tau c, it means the time taken for a chemical reaction to happen or vibrational energy to reach equilibrium is very less than flow time, then flow is considered equilibrium. And if flow time is very less than time for chemical reaction to happen, then flow is considered frozen. It means that flow is completed but chemical reaction is not even started, you can say. And if both time are comparable to each other, then flow is non-equilibrium. Or you can say, if flow is not equilibrium or frozen flow, then flow is considered non-equilibrium flow. Now we'll see the orientation of non-equilibrium flow. So here instead of general quantitative equation, we use the species conservation equation. Our species conservation equation. So let's say this is our control volume. This is one surface and cap and velocity is v here. And there is one species. So let's see. There is one species which density rho I. So mass flow net mass flow of the species I out of control volume will be double integration rho I dv dot ds. As we are in the general derivation of contradiction also. So this is the mass flow of species I which is going out of the control volume. V dot ds is the direction of the normal to the small control surface ds. And the rate of change of, okay, first we'll see mass of species I inside control volume it will be triple integration rho I dv. This volume I am writing without this vector sign and velocity with vector sign. So what will be the rate of change of species I? It will be rho I dot t triple integration v rho I dv. Now let's take wi as local rate of change of rho I due to chemical reactions. Rho I will change only due to chemical reaction. Inside control volume. So what is the rate of creation or extinction of species I will be equal to triple integration wi dv. So from the conservation, rate of change of mass of species I will be equal to net outflux of species outside of control surface and creation or destruction of species I. This is a species concentration. This is rate of change of species I not species. Mass of species I in control volume parenthesis this whole term, net outflow of species with minus term it will be net inflow. With positive term it will be net outflow, and with minus term it will be net inflow of species I, and this term will be creation or extinction of species I inside control value. This is the conjunctive equation, species conjunctive equation. If we use the divergence theorem here, then this whole equation, let's use the divergence equation for dou by dou t triple integration rho I dv v equal to, if we use the divergence in the first term on the right hand side, it will become triple integration dou dot rho I v dv plus triple integration w by dv. But one thing, we are using rate, so I will use here dot. So if we take all this together, we will get triple integration v dou rho I by dou t plus del dot rho I v vector minus wi dv equal to 0. So for it to be 0, this term should be 0. We will get dou rho I by dou t plus del dot rho I v vector equal to w. This is the species conjunctive equation. Now let's say there is some chemical reaction. So if there is some chemical reaction happening, one thing is to know that w dot I is rate of change of of mass of species I per unit volume. It was rate of change of density. So density is nothing but mass per unit volume. So it becomes like this. And if we divide this by molecular weight, it will become rate of change of mole of species I per unit volume, which is nothing but concentration of species I, rate of change of concentration of species I. So Wi, we can substitute Mi di upon dt, and this rate of change of this concentration of species I can be found from the chemical reaction. Using the chemical rate equation, instead of I, here I will write xi, and it will be easier for you to remember. This is species xi. Xi is species I, and this is concentration. So like this, we will write equation for all the species present in the system, and there is one more. We write for n minus 1 species, and one extra equation which we will take is sigma I rho I equal to rho. And we can write alternative form of this equation also. If this is constant equation, we will define the mass fraction of species I. It will be nothing but Ci equal to rho I upon rho. You can think like if you multiply the volume on upper and lower side, rho I will get the mass of species I and one total mass. So it will be a mass fraction. So we can substitute rho I equal to Ci into rho. So our constant equation was rho I upon rho t plus del dot rho I vector equal to Wi dot. Substitute rho I here, we will get rho Ci upon rho t, rho Ci into rho t plus del dot rho I 0. Ci rho P bar equal to Wi dot. We will separate this term. So we will get rho Ci by rho T plus Ci rho by rho T plus Ci del dot rho Vi plus rho V dot del C equal to Wi dot. If we take the terms with rho common and Ci common, we get rho del Ci by del T plus V vector dot del Ci plus Vi rho by rho T plus del dot rho V equal to Wi dot. This term will be 0 because this is nothing but global continuity equation. So our equation will be rho Ci by rho T plus V dot del Ci equal to Wi dot. This is nothing but substantial derivative dCi upon dt equal to Wi upon Wi dot upon 2. This is also one form of Cauchy's continuity equation. Let's write molecular masses in my bar. So mi bar is molecular weight. Okay. Let's say mass of the system is and mass of the species is mi. So we can write mole to mass ratio to mi equal to our molecular weight was mi bar. So mole to mass ratio Ni eta I equal to what will be the Ci upon mi bar. So I will substitute Ci equal to eta I mi bar. We will get d eta I mi bar upon dt equal to Wi dot upon rho. This mi bar is constant, so it will come out, so it will become d eta I upon dt equal to Wi dot upon rho mi bar. This is the alpha 1 form of species continuity equation. So our governing equation for non-nuclear hypersonic flow will be, let's say, dou rho I upon dou t plus del dot rho I p equal to wi dot. Is for n minus 1 species, and one equation will be sigma rho I equal to rho. So these are total n equations for n species. These are the continuity equation. These are species continuity equation. One will be global continuity equation, dou rho y dot t plus del dot rho e vector equal to 0. This is global continuity equation. In the species continuity equation, wi dot will be found in the chemical reaction, where wi dot is nothing but mi bar dxi upon dt, where dxi upon dt will be found from the chemical reaction. Momentum equation will be given by rho dv by dt equal to minus del p. This is for n vessel. We are studying for n vessel only currently. And the equation will be given by d rho dh naught upon dt plus equal to dou p upon dou t plus q dot. Q dot is due to the volumetric heating, and h naught is h plus v square upon 2. These are the governing equation for initial hypersonic non-equilibrium flow. So we will stop here for today, and the reference for this is taken from Hypersonic and high temperature gas dynamics by Anderson. You can refer to this book, and there is also one more book, Physical Gas Dynamics by Vincenti. Okay, so we will stop here today. Thank you.